What's going on, everybody? Welcome back to the Q&A playlist. It's been a few months since I've done an episode for this particular playlist, but we were asked three questions. And before I get started, I just wanted to dedicate this episode to Chadwick Boseman. I don't typically idolize Hollywood stars, but this man, when he was hired in 2016 to play T'Challa, he was dealing with cancer throughout the filming of Civil War, Black Panther, Infinity War, Endgame, and then all those meet and greets with fans, all the screenings, and in particular, he was visiting fans that were dealing with cancer, kids with cancer. I saw a picture of that on Reddit. Um, I, I think this man is a hero, and I just wanted to dedicate this episode to him. All right. So we were asked three questions: one about borehole geophysics, two, the second question is about the role of V's in determining dip based off of those V's, and then three, plotting drawdown curves on semi-log paper. So Jerry asked us about the borehole geophysics, and we'll only focus on the theory and not the utilization of the method, because this would probably be best coming from someone in petroleum geophysics that actually does this type of work. I haven't done anything related to borehole. Okay, so before we jump into each method, we have to kind of determine uh, the characteristics, geophysic characteristics of the common rock types that we'll face. So shale and clay will have a low spontaneous potential, low resistivity or high conductivity, high gamma, moderate density, and then this is in the way, sonic, and then high neutron. The the recording game bar is in the way of that. But whatever's in front of Sonic, yeah, it's that. So you have sandstone and sand. It has high spontaneous potential, moderate resistivity, low gamma, moderate to high density, low sonic, low to moderate neutron. You have limestone, low spontaneous potential, high resistivity, low gamma, high density, low sonic and neutron. Salt water is low to moderate spontaneous potential with low resistivity, which means high conductivity. Pure water is actually not conductive of electricity, which was surprising when I first took physics, but the electrolytes or the dissolved salts in water is what makes it conductive to electricity. Fresh water will have low spontaneous potential and obviously high resistivity in fresh water. Hydrocarbons have extremely high resistivity, and coal has generally low spontaneous potential, high resistivity, low gamma, very low density, and very high sonic, high neutron. So we'll dig into spontaneous potential first. So it can be used to determine and correlate lithology, bed thicknesses, and the salinity of formation water. It's a record of naturally occurring potentials developed between the borehole fluid, the formation water, the surrounding rock materials as a function of depth, as well as the temperature and type or quantity of clay. And it's plotted on a vertical column or tract. Uh, Typically on the left hand side, it's typically in unison with a bunch of different methods. It could be run with gamma, it could be run with resistivity, and it's in millivolts per inch. So this kind of shows you what a spontaneous potential log will look like in just basically a shale sand interbedded sequence. This particular sands you have gas in them, but and it'll show you the difference. Shell has a high resistivity, spontaneous potential, not resistivity, and sand has a low spontaneous potential. And as you see it varies. Sand will kind of increase in resistivity as it increases in saturation. Shell pretty much stays the same. And then once you get gas, it decreases a little bit. It'll be between those two. And then if it's thick, shaly gas sand, resistivity will be the highest. I keep saying resistivity. It's spontaneous potential. Sorry. Okay, so spontaneous potential deflections are recorded as negative to the left and positive to the right. And an example is when formation water of the sand shell sequence is more saline than drilling mud, the deflection in sand is negative. And obviously, all these deflections on this side are negative, SP. So a line drawn through the extreme positive deflections on an SP curve for standard salinity relationships is called the shell line or the baseline, which is this line right here. And it's basically the max deflections in a log. And if it's constant, the baseline will just be vertical. It won't have this angle to it. It'll just be completely vertical. And then a line drawn through the extreme negative deflections, which is on this side, is called the sand line. So you see it right here, 3 different sand lines. So the limitation to SP logging is salinity differences between the borehole fluid and the formation fluid in freshwater environments. So a rock that was deposited via a river, like a conglomerate or something, or a shell, it can be considerable. So this kind of shows some examples of the deflection types. So as we said, shell has high deflection, and as you get into the sands, it decreases significantly, and then shell obviously goes high again. Sand decreases, shell increases. Limestone has a positive deflection if it's tight. It has a positive deflection, but less than shell. And if you have a sandy shell, it kind of gives you this pattern, this edgy, jagged edge deflection. And if a layer is thick, a broad deflection will occur. So kind of like this. That would be a broad deflection. And if the layer is thin, a deflection is going to be a narrow peak. There's not really any narrow peaks in that one. But so how do you think, I would pause the video at this, how do you think this lithologic column will look on an SP log? So you have shell, sandstone, dolomite, and shell. So you would expect this to be high deflection, or start off high over here, and then it will decrease at the contact, stay like this, and then increase as you get into shell, decrease as you go into the sandstone, same pattern. And then dolomite, I don't exactly remember, but that's a limestone, so that should be a slight decrease, but not as negative of a deflection as the sandstone. So we'll go about right here, and then an increase. So let's see how we did. So you had the high deflection, it decreases significantly, and then you go into the contact of the shell, high deflection, same pattern. And then so dolomite actually has a pretty similar deflection to sandstone, although different pattern in comparison to this. But so that's a good way to practice these, is to kind of just create a lithologic log and go through all of them and just try and remember how the deflections will look on these logs. And this will be something I'll have throughout the entire PowerPoint just to practice. And do we have a thin layer? This is probably the thinnest layer, but an extremely thin layer of shell, like we were talking about in the last slide, will just be one peak. Just one peak, and then it'll go back, or yeah, if it's a thin layer, it'll just be one extremely positive deflection, and then if it's grading into dolomite, it's going extremely negative. Okay, so we're digging into resistivity now. So resistivity logs can be used for lithologic interpretations, water quality, locating the freshwater saltwater interface in coastal aquifers, because they have different conductivity characteristics. They determine hydrocarbon saturation in oil and gas wells because hydrocarbon has a high resistivity, extremely high. And resistivity is the ability of a substance to impede flow of electrical current itself, and it's the opposite of conductivity, and it's in ohms per meters, if you remember from your electromagnetics physics class. So water-bearing rocks are 1 ohm meter to 10 to the fifth power ohm meter. The porosity, the chemistry of the water filling the pores, is of greatest importance, and the greater the porosity and amount of formation water, the lower the resistivity, which means higher conductivity. Salinity of the water is the most important in determining resistivity, because if you have highly saline water in the formation, it's going to be highly conductive, low R. If that makes sense to you guys, hopefully it does. Shale has high porosity and low R, so it's going to be typically less than 20 ohm meters. Sandstone, limestone, and dolostone have a higher R value than shale, and they depend on pore volume and content. Evaporites and coal have a very, very high R, and they're impervious and low porosity. And R values of sedimentary rocks tend to increase with age, and that's because porosity decreases through burial and compaction. So we're going to do a similar exercise, I guess we can call it. We're going to do one for the resistivity log. This one I did not practice enough, but so R should have a negative deflection or low deflection, so it should be on this side, and then it should increase as you go to the sandstone, and then decrease. Yeah, it's going to be the same, kind of the same pattern. You have porous, so that's going to have a lower R, I believe. It's going to have a lower R, but shale has a high porosity, so that's going to be, let's see. So at most, it's probably just going to increase a little bit and just do this pattern. And in a tight sandstone, that probably means less porosity, so not as big of a change between the shale and the tight sandstone. You'll still have a change, and then it'll go back, and then you'll go back to the porous sandstone, and it'll just have the same pattern. So let's see. So yeah, as you can see, it's negative deflections at all the shale beds, and then the porous sandstones kind of vary. The tight sandstone has the highest R, well, I guess past this one, and it's probably because, yeah, this one has the highest R, or it starts decreasing, because it has salt water here. Yeah, and oil has a very high R, so that's probably why this is at its highest point. So I hope this makes sense to you guys. All right, so we're getting into gamma now. So gamma ray is used to determine shale content. It's used to correlate stratigraphy and lithology, and to evaluate radioactive deposits such as uranium. High energy electromagnetic waves emitted by potassium-40, uranium-238, and thorium-232 isotopes. It indicates the amount of natural gamma radioactivity present in the formation versus the depth. That's typically how it's plotted. The amount of radioactivity present increases in the following way. Granite would have the highest gamma ray readings, and then it goes all the way down to anhydrite and gypsum, which are evaporites, and that would be your lowest. Pretty much all the sedimentary rocks are in the middle. Shale, gamma ray is typically used for shale. So what do you guys think this log will look like on the left? Let's see. So shale should have a medium deflection. Paleosol, that should have about the same, maybe a decrease. Yeah, it's nothing too crazy. So this is how this one would look. So you have a high deflection, and then I skipped the coal. Yeah, so coal has a low gamma, so it decreases significantly, increases as you go into the blocky mudstone. It kind of stays consistent until you get to coal. It doesn't decrease like the previous coal, probably because it's more compacted, or maybe it's lost some of its gamma signature. And then you have interlaminated sandstone and siltstone, so the pattern kind of changes there. But like I said, this is the best way to practice this type of stuff. I highly recommend it. So neutron logging, it measures porosity in petroleum and hydrogeologic investigations. You record the neutron interactions that occur near the borehole. Most of neutron interactions are due to the amount of hydrogen present due to the water content of the rocks. Hydrogen is the most effective element in moderating neutrons because they have the same mass. And what do you guys think the neutron log will look like on the right? So we have the gamma, but let's see. So I would expect shell to have a low density. Let's see. I'm trying to remember. No. Well, I guess we'll see. I would pause the video and try and guess. So, let's see. We're on neutron, so the black line. So, shell actually has a low density, and it increases significantly at the halite, and then decreases at the shell, and hydrite, high density, and decreases significantly once you get to shell, and decreases even more once you get to the gypsum layer, and then it increases again once you get back into the shell. And this is a good one to practice with density. Density as well. So gypsum and coal produce large false deflections. Shell and clay have large deflections indicating high porosity. So the caliper logging is basically just measuring the borehole diameter. We don't really have to practice that. Basically, it just shows you when it's at its largest and when it's at its smallest. You're just making, it's kind of a way to make sure you're not having collapse of the borehole. Density logging, it measures the density of the rocks used to determine porosity. And shell has a high density, and then it decreases significantly in the sand, increases again. Oh, wait. Okay, so I'm flipped around, right? No, okay. Never mind. I was right. Okay, high density, low density, high density in the shell, decreases, and the gas kind of lowers the density of the sand, and then once you get into the liquid, it increases a little bit, and then once you get back into the shell, it increases. And then when it comes to sonic, it measures the transit time of the formation to determine the porosity, the correlating units, and the facies analysis. It can be used in mineral exploration as well, and this is what a sonic log will look like. Let's see. So it'll move its fastest through shale because of its high density, and then sandstone has kind of a lower density than shale, and that's pretty much the pattern. Limestone kind of has a weird pattern to it when it comes to sonic logging. Dolomite, kind of a similar pattern to limestone. Okay, so the rule of V's, we had Jamie ask us about the rule of V's and determining dip off of a map, and I couldn't find a good map for to do an exercise, but we'll run through this. Critical to accurate interpretation of geologic maps, and the rule states that a V made by a geologic unit crossing a stream, valley, will point in the direction of the formation that underlies the valley. You may be able to infer general strikes and directions of dip using this principle. So, well, we'll go through the rules on this next one. Okay, so horizontal bedding, which is this one right here. It V's upstream, and the bedding planes are parallel to the topo lines. Dip upstream, which, let's see, it V's upstream and outside of the topo lines. which I believe is this one.
Yeah.
So when you have dip upstream, you have a V upstream, and that's A, and it's outside the topo lines. Vertical bedding just straight cuts across the valley. That's F. And then dip downstream. When the dip downstream is greater than the valley gradient, you get a V downstream. So this one right here, E. And then dip downstream less than the valley gradient, it V's upstream inside the topo. So this one here. And then you also have a situation where they're equal to each other, the dip downstream and the valley gradient, and that would be this one right here, where there's no V shape. So if the rule of V's is applied to a map that has outcrop patterns of geologic units, the topography and the bedding attitudes are not provided. It'll V upstream in 3 cases: dip upstream, dip downstream, gradient is less than the valley gradient, and horizontal bedding. It'll V downstream when the dip downstream is greater than the valley gradient, and it won't V if you have vertical bedding or the dip downstream is equal to the valley gradient. So I highly recommend this book to practice rule of V's and other mapping problems. I highly recommend buying this book right here. I used it to prepare for my exam. It goes through everything that is covered, like 3-point problems, calculating dip, apparent dip, all that. Highly recommend it. But so to determine dip, you can use the 3-point problem, which is described in another video, or you can utilize mathematics. And mathematically, dip can be determined by using the tangent. Dip equals to the rise over run, and rise is the vertical elevation change, usually measured from strike elevation to low point elevation, and the run is horizontal or map distance over which rise occurs. So to figure this out, you find the rise and the run, you divide those, and then you take the inverse tangent of that number that you get, and that'll be your dip. Okay, and then this is just another graphic to kind of show the rule of V's. You could pause it if you want and check these out. Good visual. So the third question that we were asked was plotting drawdown curves on semi-log paper, and this is what semi-log looks like. And when you do particle distribution curves, this is the type of paper that you use. You also use it for drawdown. It's logarithmic in this axis, the x-axis, and equal intervals in the y-axis. And I reference an introduction to well drawdown to explain drawdown. You can Google it, and it's a good read. So what is drawdown? It is the drop in water level in a well when the water is being pumped and it's measured in feet or meters. Why measure drawdown? So you can make sure your source is adequate and not being depleted. You can tell if your supply is slowly declining. Early detection can give you time to explore alternative sources, establishing conservative measures, obtain funding. It can give you information about performance and the efficiency of wells, and it can combine with well yield, and it can tell you if the well screen is being encrusted with like calcite, caliche. So a couple definitions. We already defined drawdown, but static level is the level of water in a well when no water is being pumped. The pumping level is the level of water in the well during pumping. Well yield is the volume of water per unit of time that is produced from the well by pumping, and it's measured in gallons per minute, gallons per hour, or cubic feet per second. And specific capacity, well yield per unit of drawdown. So if a well yield is 100 gallons per meter and the drawdown is 10 feet, specific capacity is 10 gallons per meter per foot. Okay, so you must know the distance from the surface to water level in the well. So you measure to the groundwater level using a water level gauge, And the 3 steps to calculating the drawdown is you find static level. After you turn your pump off, after pumping it, you let the well fully recover, and once it reaches its max, that will be the static level. To find the pumping level, pump until the well reaches constant pumping rate or filled. Measure the depth to water at regular intervals until water level stops dropping, and that's your pumping level. To calculate drawdown, you just subtract static from pumping level. So say your static is 65 feet, pumping is 72, your drawdown is 7 feet. So further reading, these 2 websites, just Google Thies and TWDB and Thies Actuasolve, however you say that. It allows you to play with numbers and observe curves as you change the numbers, and this will give you more mathematical explanation of the curves. 2 good websites to check out. And then another good read is Understanding Diagnostic Plots for Well Test Interpretation by Renard, Glens, and Miguel. Let's just say Miguel. Okay, so to me, the best way to try and practice drawdown curves is to kind of make your own in Excel. I don't have semi-log paper, but you can do your own in Excel. Just make up numbers and try and understand how these curves change. And as you practice these, you can start plotting on the paper as you come to an understanding of how how Excel is doing it for you. Obviously, time is the one that we're putting into log, and feet, which is along the y-axis, we are not putting that into log. Yeah, and then that's how I plotted it. And when you plot it on the semi-log paper, I mean, you can do it in Excel and just put this entire column in log, and that'll give you the numbers you need to plot it on the semi-log paper. And I appreciate you guys watching. Until next time.